Solar panels are modules that use photons to generate electricity. They are able to utilize one of the most abundant renewable resources on Earth, sunlight, and as such are very significant in the field of sustainable energy. In the US alone, solar panels are able to offset more than 70 million tons of carbon per year. Today, we will be analyzing flat solar panels for at-home use with calculus and trigonometry. So where do we begin? We will first start with the amount of energy a panel can actually produce. Firstly, we know that power is defined as the rate of energy production. This means that P is equal to dE divided by dt, where power and energy are functions of time. We intuitively know that the energy production of a solar panel is greatest when the sunlight is hitting the panel from directly above, as that is when the panel is actually receiving the most light. At such a position, the sun would have an angle of elevation of pi over 2 radians relative to the panel, which means our function for power has a local maximum at pi over 2. Thus, the panel of a power is equal to C times sine A, where A is the angle of elevation of the sun, and C is a constant that is attributable to the efficiency of the panel. However, for simplicity's sake, we'll just say that P is equal to sine A. Knowing this, we arrive at the differential equation sine A is equal to dE over dt. We can rearrange this to dE is equal to sine A dt. Therefore, by the fundamental theorem of calculus, energy is equal to the definitive integral of sine A from t1 to t2, where t1 and t2 are times during the day. Power is also defined as a rate of energy, so sine A will equal dE over dt. This equation, sine A is equal to cosine of L times square root of quantity 1 minus sine squared of small a times cosine squared of 2 pi large T divided by 365. That quantity times cosine 2 pi small t divided by 24, plus sine of L times sine of small a times cosine of 2 pi large T divided by 365. Say that one 3 times fast. Is a very long equation we obtained from a research paper that allow us to find sine A. In this equation, L is the latitude of a place on Earth, small a is the angle of Earth's axis, large T is the time of year measured in days from June 20th, and small t is the time of day measured in hours from noon. In short, we can calculate P given the time and location of our panel. This equation doesn't account for certain environmental factors and assumes ideal conditions. Now that we have our equation, we can go about solving for the energy that can be produced in a day. First, we'll need to find the times of sunrise and sunset to bound our integral. Solar panels only produce energy when there is daylight, which means their activity is bounded by the times for sunrise and sunset. At the exact times of sunrise and sunset, the angle of elevation of the sun is 0, which means our solar panel will have no power. Knowing this, we'll equate sine A to 0. For the purpose of this example, we will place our hypothetical solar panel in Fremont on May 28th. Fremont has a latitude of 37.5485 degrees. Our large T is equal to 342 on May 28th, and the tilt of Earth's axis is 23.44 degrees. We can now plug these values into the equation and solve for small t. Because t is an angle within the argument of cosine, we'll have two different possible values after isolating it with arc cosine. In this case, we end up with small t is equal to 7.29 or negative 7.29. Because our equation is set up such that small t equals 0 is noon, small t equals 7.29 must be the time of sunset, while small t equals negative 7.29 is the time of sunrise. Since you're using a 24-hour cycle, small t equals 24 is the same as small t equals 0, both times being noon. Therefore, the time of sunrise is 12 minus 7.29, or 4.711. This translates roughly to 4:43 a.m., while the time of sunset is approximately 7:17 p.m. When we account for the shift in time due to daylight savings time, our time of sunrise and sunset are 5:43 a.m. and 8:17 p.m. respectively. Online sources say the interval of daylight on May 28th in Fremont is 5:49 a.m. to 8:21 p.m., so our times are sufficiently accurate for our purposes. Now we can calculate the total energy produced in one day by using the lower and upper bounds, small t equals 16.711 and small t equals 7.29 respectively. We can now use these bounds for the definite integral in the equation for energy. By plugging all these values into our initial equation, we get that E is equal to 8.577. In order to maximize the amount of sunlight that the panels absorb, we will tilt the panels perpendicular to the sun at noon. The angle of elevation of the sun at noon in Fremont on May 28th is 74.13 degrees. Therefore, the tilt of the panels will be 15.87 degrees. To find the energy produced by a panel over several days, we can set the bounds of the integral into functions. The upper bound will have a function that displays sunset, while the lower bound will have a function that displays sunrise. According to this diagram at the website below, we can see that the times of sunrise and sunset resemble upside down and right side up cosine functions respectively. Therefore, the upper bound can be represented by a function that displays sunset, while the lower bound is represented by a function that displays sunrise. E of t is the amount of energy produced on a given day, so by integrating E of t, we will get the energy produced in a given time frame of days. Therefore, our function for finding the total energy over multiple days is as follows. Definite integral from large T1 to large T of the quantity of the definite integral from small t1 to small t2 of c times p of small t d small t, that quantity times dt, where p of small t is the expression for power and c is the constant unique to the specific solar panel.